Hello everyone. Today I will be an auto electrician and I'll start with some background. But first, meet my son. He's 6 years old and he has his own car. He was riding this car until I got tired of charging the lead batteries of this little car every half hour. Yes, the car has its own charger, but it takes an awfully long time to charge. It's much faster to charge with a lab power supply. One fine day, Dad got fed up with it all and decided to install a high-capacity lithium-ion battery in the car. And everything would be great, because the capacity of the new battery is much higher than the old one, allowing for much longer rides. But apparently, due to overheating or something else, the car's power switches started failing. One after another, the contacts got burned, and so on. In short, since Dad knows a bit about electronics and can handle a soldering iron, he decided to take this car, throw out all the internals, leaving only the motors, and do everything his way, with quality, reliability, and heart. And most importantly, to radically change the control principle of the car, and make everything exactly like in real cars. About the car itself. It was bought a long time ago, about 4 years back, and was actively used. The car is, of course, electric, with the ability to be remotely controlled by a remote. There are 2 motors, one for each wheel. The rear wheels are the driving wheels. The steering wheel is also equipped with an electric drive. The build quality of the car is mediocre. All the controls are located under the seat. There are headlights with low-power local bulbs, which are purely for show. Naturally, they can't illuminate anything and light up when the car is moving. There are 2 speed modes and a pedal. Press it, you go. Release it, the car stops. And other switches, such as the power switch, the toggle for switching control between the remote or the driver, and various sound signals and flashers, which were powered by separate batteries. My task, as I already mentioned, is to remove everything, leaving only the motors, and then implement everything in my own way. The modification will only affect the electrical part. I won't be upgrading the appearance or mechanical parts for now. Let's start, perhaps, with the battery. The machine was powered by 2 6-volt lead-acid batteries connected in series. If memory serves, their capacity was around 10 amp hours. The original batteries failed a long time ago, and eventually, the child was riding with a 12-volt, 7.5 amp hour battery from a UPS. The new battery will be like this lithium-ion. The voltage of the battery when fully charged is 12.6 volts, or 10.8 volts nominally. The battery is 3S8P, meaning 3 cells connected in series, each consisting of 8 parallel connected cells. The capacity of this new battery is about 15 amp hours. The power cells of the 18650 standard are welded together using nickel strips. I assembled this battery a long time ago for other purposes. The cells are placed in holders, with sealant between them. Overall, everything is assembled according to the standards. By the way, the cells are regular, not high current, but they are branded from laptops. High current cells are not necessary in this case, as such a battery can easily handle currents of up to 40 amps and more. And for our purposes, this is with a 2-fold, or even 3-fold, margin. The battery is supplemented with a charge protection and cell balancing board. This board is only rated for 25 amps, and it will be more than sufficient, but I have already ordered a new board for 40 amps. Once it arrives, I will definitely replace it. Regarding the functionality of this board, it disconnects the battery in case of deep discharge, overcharge, and short circuits. It also balances the cells by equalizing the voltage on them. Real tests have shown that this battery provides autonomous operation of the vehicle for about 4 hours with a payload of 15 to 20 kilograms in the form of the driver. Unfortunately, I did not measure the weight of the vehicle itself. The battery connects to the machine through a standard XT60 connector in their pair. The wires from the battery are soft and heat-resistant silicone insulation, a pair for the positive and a pair for the ground. The electronic part or control board. The control system was implemented based on a PWM regulator, the schematic of which I found online. Apparently, it is quite old. Of course, modifications were necessary. Specifically, the power of the circuit was increased significantly, and in the original power supply circuit of the internal driver of the PWM controller SG3525, which is pin 13, it is taken from the internal reference source. That is, the driver is powered by 5 volts. This will result in powerful field effect transistors not being fully open, causing them to heat up significantly and potentially burn out. In my case, the driver's power supply, and consequently the gate voltage, will be around 11 to 12 volts, and is taken from the linear regulator 7812. I added this regulator purely because I initially wanted to power the machine from a 4S battery or 16.8 volts. And the PWM controller with the driver were supposed to be powered by a 12-volt regulator. But with a 3S power supply, the regulator can be omitted. Other modifications involved increasing the soft start time, recalculating and strengthening some components, as well as reducing the PWM operating frequency. In general, the higher the frequency, the harder it is for the chip to manage the switches. In classic PWM speed controllers, the operating frequency ranges from 2 to 10 kHz, which is within the audible range. But in this case, it's not critical at all. You might also have noticed that the power switches are controlled without an additional driver, but the chip itself has a powerful repeater, and it handles it quite well. Diodes are installed at the outputs of the chip. The fact is that the duty cycle on each output is no more than 50%. That is, if you use one output of the chip, the power will range from 0 to 50%. And this solution provides regulation almost up to 100%. I forgot to mention that the circuit is equipped with protection against short circuits and overloads. It is built on the basis of a current sensor, which needs recalibration depending on the desired current for the protection to activate. It works like this. If the consumption at the device's output exceeds the limit set by the current sensor, the voltage drop is sufficient to trigger a low-power transistor. This voltage is approximately 0.6 to 0.7 volts. When it turns on, this transistor grounds the 8th pin of the PWM, causing the PWM to stop generating a signal. The power switches close. It is necessary to carefully calculate the current sensor based on Ohm's law. For example, in our case, considering the sensor's resistance, the required voltage drop across it will occur when a current of about 30 amperes flows through it. At the same time, it is also necessary to calculate the maximum power dissipated on the resistors. Based on this, it becomes clear that in our case, the sensor will dissipate about 18 watts of heat. But this is the absolute maximum. During average driving, the heat dissipation will be 2 to 4 times less. In any case, our sensor consists of 5 resistors of 5 watts each, meaning it can handle up to 25 watts. So we have a double margin. The PWM controller is supplemented with a reverse diode. In this case, it's a 60 amp ultrafast STTA 6003 assembly, which is designed to suppress inductive kickback from motors. During operation, the assembly will heat up, and it needs to be mounted on a heatsink, just like the MOSFETs. And yes, 60 amps is overkill, but we have a special client for whom nothing is spared. For the same reason, we have these monstrous 75 volt and amp RF 2907 MOSFETs with a very low on-state resistance of 4.5 milliohms. And there are a couple of them here. A few words about the other components on this control board. We have a 40 amp relay. When the main switch is closed, power is supplied to the control board, but nothing starts until the ignition is activated with the key. In this case, power will go through the diode to the power relay, and it will activate. By the way, the system has reverse polarity protection. If you mix up the battery's positive with the ground, the diode simply won't open and the relay won't activate. An error indicator will light up on the board. If everything is fine, the green indicator lights up. Next, until we press the gas pedal, which is a variable resistor, the PWM won't be generated and the car won't move. The forward-backward movement direction is implemented through a pair of 20-amp relays. There is a shift lever on the dashboard. Here it is on the diagram. I think it's clear here two positions of the switch. In the first position, one relay will activate. In the other relay will activate, providing polarity reversal for the motors and consequently changing the direction of rotation. The ignition lock was originally cheap, toy-like Chinese, and it broke without working for even a second. The contacts just fell off. In the end, a real car ignition lock was installed, which was slightly modified to fit into the dashboard. But there's not much to explain here. You insert the key, turn it, and you can drive. The power traces on the control board are reinforced with single-core copper wires and are generously tinned. Overall, everything is good. Since the board will be mounted under the seat, where everything else is located, including the battery, I decided to coat this board with varnish on both sides, as this compartment will be frequently opened for maintenance and battery recharging. Yes, I haven't made the charging connector or built the charger yet, so to charge the battery it needs to be removed or charged in place, but this means having to bring the charger to the car each time. The gas pedal. I thought about this component for a long time. The original pedal is nothing more than a regular button without a latch. Press the pedal and the car moves. But I wanted to make it like in real cars. The harder you press, the higher the driving speed. In our design, the gas pedal is a variable resistor that increases or decreases the PWM signal, thereby controlling the motor speed. Earlier, I bought a collector motor with a pedal from a sewing machine at a flea market. The pedal is, of course, bulky, but the execution is excellent. Of course, it can't be used without modification. In general, I discarded all the internals, leaving only the mechanical part, the levers and the return spring. Next, I disassembled the remote control from an RC car and extracted the necessary part, the lever with a variable resistor. This mechanism essentially converts reciprocating motion into rotational motion. So I fitted all of this into a sewing machine pedal, and this is what I got. It's hard to come up with something better. Thus, our electronic pedal is ready, but it has one problem. The thing is, the mechanism from the remote control that I used here can move, both forward and backward. That is, in its resting state, the variable resistor is in the middle position. In our case, the resistor needs to be in one of the extreme positions, otherwise the machine will move, even if the pedal is not pressed. I solved this problem both mechanically by modifying the levers and electronically by selecting the appropriate resistances in this circuit. In the end, the pedal was adjusted and everything works as it should. However, the PWM is not from 0 to 100%, but from 0 to 90, and this limitation was introduced by me. The wire that runs from the pedal to the control circuit has double shielding, plus a protective corrugated sleeve. At the very beginning, the idea was simply to adapt a button from a screwdriver here, but later I abandoned this idea for two reasons. First, most of these buttons do not have very smooth adjustment. And second, the cooling of the power switch in such buttons and the switching current may be insufficient, in some cases for operating a pair of motors like the 550 type. Besides, a button from a screwdriver would actually be more convenient. Everything is ready, and you don't have to worry about the reverse. Indicators. The car has a dashboard, but as you understand, these instruments don't show anything because they are just stickers. But if you're going to bother, then go all out. Therefore, it was decided to integrate real analog meters here, which will show the battery voltage and the current consumed by the car. I found a couple of gauges at a flea market, but unfortunately, even though they are round, they wouldn't fit here, without modification. The gauges I had weren't the ones I needed, so I didn't hesitate to modify them, creating a new scale, But then I gave up on all that and installed square analog gauges for the required current and voltage. The voltmeter with the scale up to 30 volts shows the battery voltage. It only activates when the main switch is turned on. An ammeter up to 30 amps. In reality, the maximum current consumed by the machine can reach up to 35 amps, but that's in theory, if you fully load the motors and honk the horn at the same time. Otherwise, a 30 amp indicator is more than sufficient. The average current consumption while driving is no more than 60 amps. The shunt for the ammeter is installed directly on the positive terminal of the battery, or more precisely, it will be installed currently. The necessary shunt is not available. Otherwise, a standard 30 amp shunt with a 75 millivolt drop should be used here. Headlights. The original headlights were more for decoration, a pair of low-power incandescent bulbs that would light up if the car was moving. They had no effect. Once upon a time, I drilled a couple of holes from below, installed reflectors, and inserted bright white LEDs. I powered them with a pulse current stabilizer. An additional switch was adapted for turning on the headlights. Regarding the new headlights. This time, there were more complications. 12 bright 5mm white LEDs for each headlight. Each pair of LEDs is connected in series, and they are powered through separate current limiting resistors. In the schematic, I drew only 3 LEDs to save space. In reality, each headlight has this kind of schematic. All of this is on their own printed circuit boards. In general, it's done according to feng shui. I also found a couple of lenses, which I glued using B7000 adhesive. It didn't turn out great, but it looks impressive, especially in the dark. Besides the main headlights, there are also LED indicators purely for aesthetics. They all turn on together with the press of the main switch responsible for the headlights. The headlights can only be turned on if the central power switch is activated. The power of one headlight is about 3 watts. It actually shines quite decently. Switches. I'll start, perhaps, with the fact that the main one is the central 35 amp Soviet reliable switch. It directly disconnects or connects the battery. If this switch is open, the car is completely de-energized. If it is closed, only the alarm and headlights work, and the rest of the car comes to life only after the ignition lock is activated. As I mentioned earlier, initially the ignition lock was a toy, later replaced with an automotive one. In fact, this lock activates a 40 amp power relay located on the control board, meaning it supplies power to its coil. It is through this relay that power is supplied to the PWM controller circuit, which controls the motors. The headlights have a separate switch, which is located in a rather convenient place. Next to the voltmeter, there is a switch styled like a gear shift lever. In reality, this is a switch that determines the direction of the car's movement, forward or backward. The construction is simple. A regular Soviet toggle switch with an extended lever and a ping-pong ball at the end. For reliability, the ball is filled with epoxy resin, and the lever itself is securely embedded in the resin. Well, kids, they managed to break, even the unbreakable. I hope this construction will last for a reasonably long time. Another switch, or rather a button, is located on the steering wheel. I installed this button here a long time ago. It controls the horn, or more precisely, it supplies power to another power relay. And that, in turn, activates the horn. The horn. Well, regarding the control of this part, I think everything is clear. Press the button, and the car honks. But the horn here is by no means a toy. In certain circles, these horns are quite popular and are known among car enthusiasts as Armenian Bosch. Rewound, reinforced, and incredibly loud. Why install such a horn on a children's electric car? Initially, I wanted to install something simpler, but the owner's wish is law. The kid demanded a horn, like the ones in real cars. If someone honks this nearby, you'll go deaf for a moment, and then have ringing in your ears. So, a lot of time was spent adjusting this thing to keep the sound at a minimum. In the end, this is how it sounds. Beep, 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 beep. There's only one emitter, and it was installed at the front. I think it looks nice. The wiring and installation overall, what can I say? Corrugated tubes, sealant, nuts, plus, lock nuts everywhere. Even though it's a children's car, the installation is quite serious. Powerful Soviet terminal blocks on non-combustible bases, reliable stands, everything is labeled, and there's even a diagram under the seat. Many switches were partially or fully sealed before installation. The wire gauge is chosen with a significant margin. The wiring is copper. The minimum wire gauge for low current lines is 1.5 square millimeters, while the maximum gauge for high current power lines, which will carry up to 20 amps of current, is 4.5 square millimeters. There is electronic protection against short circuits, deep discharge, and overcharge for the battery. And all this is ensured by the appropriate protection board. Another electronic protection is on the control board itself. This protection will shut off the motors during heavy overloads and short circuits. There is a soft start for the motors. I included this option for a reason. The thing is, if the car is on a slope and you suddenly put it in reverse, there's a chance it could tip over. The soft start prevents the car from starting abruptly. The power terminals are on a non-reversible base. There is also protection against incorrect battery polarity. If you mix up the positive and negative, nothing will work, and an error LED located on the control board will light up. Overall, the safety here is well taken care of. Conclusions. You might say you should add shock absorbers, rubber wheels, and so on. I had a lot of ideas in mind. I wanted to make a folding roof with an electric drive. At one point, I even decided to turn this car into an amphibious vehicle, but then I came to my senses and told myself, this is a children's electric car. The little one will grow up, and the car will end up in the attic. He'll probably remember this car when he has kids of his own. But I consider my task accomplished. Everything drives, lights up, and adjusts, as planned. And that's the final word. The entire modification, development, soldering, and everything else took a week. Now I kind of regret it. In that time, I probably could have built a cooler car from scratch with a metal frame and all the amenities. But in any case, what's done is done. And the little one will ride and enjoy a relatively unique and fancy car. That's exactly what I was aiming for. With that, I conclude the video. I remind you that all the source files can be downloaded along with the project's complete archive via the link in the description. Share this video if you liked it. Follow me on Instagram. And as always, this was Kazyanov K, with you. Until next time, goodbye.